what we are going to do in this video is we're going to start with a 3-point problem. We're going to make some strike lines additionally to draw a little bit of an outcrop pattern, and then we're going to talk about how we would use something like that to determine the apparent dip that would be perceived across a cross-section line. So let's start with the 3-point problem side of this. We've got 3 points, A, B, and C, and we know from drilling data that unit A, or that these 3 points lie on the contact between 2 units, and that A, they had to drill 100 meters to locate it, that B, they had to drill 20 meters below the surface to locate it, and that with unit C, they had to drill 200 meters below the surface to locate it. So A is on this contour for 1,100 meters. If they had to drill down 100 meters to locate it, then A is actually at a depth of 1,000 meters. If B is 20 meters below the surface, let's go over to B, it is on the 700 meter contour, then that means that B is actually at a depth of 680 meters. And if C is 200 meters below the surface, and here C is at being drilled down and reached from a depth of 1,000, then C, or an elevation of 1,000, then C is actually at 800 meters. So on the surface, while it might seem like A and B are actually the farthest apart, or sorry, A and C are the most similar in elevation. Oh, they really are most similar in elevation? Never mind. Sorry, guys. Okay, so those are our actual elevations for these units, are these numbers over here. So now what we're going to do is we're going to determine the strike and true dip of the unit boundary. So we're going to go from the highest elevation point to the lowest elevation point. So again, this is going from 1,000 meters down to B at 680 meters. So we're going to connect these 2 points with a straight line. And we're going to determine the apparent dip along that line. We're going to do this using a triangle method. So we're going to draw a right triangle where the height of that triangle is the difference in height or difference in elevation of these 2 units. So we're going to do 1,000 minus 680. That gives us 320 meters. And then on the long leg of this triangle, not the hypotenuse, but this bottom side, we're going to put the horizontal distance between the 2. So what we need to do is come up here with our ruler and measure that scale. And we get every 13/16 of an inch is 500 meters. So every 1/16 of an inch is going to be 38.5 meters, and every 1 inch is going to be 616 meters. So let's measure this horizontal distance down here now. Okay. We get 3 inches and 1/16, and I'm sorry I'm using a mix of units. It's just the ruler that I have on me today. So 3 inches is this times 3 plus 1/16. Grab a calculator. All right, so 3 times 616 plus 38.5 should give you 886.5 meters below. And now we're going to calculate the apparent dip. So we're going to try and get this angle, which is the same as that angle. So we're going to get this apparent dip. We're going to use tangent, and actually inverse tangent of opposite over adjacent. If this video is moving a little bit too fast for you, go back to my 3-point problem video and see about that before you try this one. So we're going to do inverse tangent of 320 divided by 1886.5. Make sure your calculator is set to degrees. And you should get 9.6 degrees. That is not the true dip. Again, that's the apparent dip. So if I were if I were driving my car down a road right here and I were looking at an outcrop oriented in this direction, the dip I would see of the unit would be 9.6 degrees. So let's find the true dip. So the way we're going to find true dip is starting with strike. To get strike, we're going to use this point C. So C, we had decided, was at an elevation of 800 meters. So somewhere along this line of this triangle, we're going to hit a depth of 800 meters. So starting at 1,000, we're going to hit 800 at some point along that line. Okay, so the way we're going to do this is to draw another triangle. I know I want the point to be at 800 meters, so 1,000 minus 800 is 200. That's the elevation difference I want between A and the point I'm going to get to, which I'm going to call C prime. That's the height difference. And then I'm trying to find this horizontal distance. And I know I'm moving along this line, so my apparent dip is 9.6 degrees. So I'm going to say tangent of 9.6 degrees is opposite over adjacent, which is what I want, and I'm going to multiply by x, divide by tangent of 9.6 degrees. So on your calculators, do 200 divided by tangent of 9.6 degrees, and you should get 1,182.5 meters. So that's that horizontal distance. Now we need to convert this to the scale of our map so that we can actually draw that point in. All right, we know that every 600, actually let's use the 16ths. So we're going to divide this by what we would have for 1/16 to find how many 16ths of an inch we're going to need. 1182.5 divided by 38.5. I get 30.7. We're just going to round that up to 31. So that is 31/16. So almost 2 inches. And that's moving from A to that other point. So if I went all the way out to 2 inches, 2 inches would be 32/16. So I'm just going to come in 1/16. That is the point C prime. And I'm going to connect C prime and C. Oop. Okay, so from C to C prime, this is the direction of strike. And if you've already watched the strike line video, C is at a depth of 800 meters. We can call this the 800 meter strike line. So now we can measure dip. What we're going to do is dip is going to be perpendicular to strike. So starting at A, we're going to drop a line perpendicular to strike. A little off on that. Okay, so it's this one right here. All right, that line represents the direction of dip. So now we need to use that triangle or that line to produce a triangle that gives us true dip. We already know that the difference in elevation between A and the 800-meter strike is 200 meters. This time we want true dip, and we can measure the horizontal distance. So I get, all right, this would be 16 sixteenths, 8 sixteenths, or let's see, 16 plus 8 is 24, 25, 26, 27, 28, 29. I get 30 sixteenths. And I need to convert that to meters. So I'm going to multiply 30 by 38.5. So those are, I get 1,155 meters. And now I can use tangent or inverse tangent. Inverse tangent of opposite over adjacent. On your calculator, you're going to put in atan of 200 divided by 1155 in degrees. And I get 9.8 degrees. So not that far off from our apparent dip. Okay, and the reason for that is that, see how this angle is pretty small? Our strike line, or this line that we were viewing across, is almost already perpendicular to our strike line. And when we view dip perpendicularly to strike, we view true dip. So this is our true dip, is 9.8 degrees. And because this is 1,000 and this is 800, this is decreasing in elevation. Our dip is to the southeast. So let's take a second and just write strike and dip. I'm going to draw a vertical line. I'm going to measure this value. Oops, sorry. Get 41, 42, 43. So I get 43 degrees. So if we were going to write strike and dip, we could write north 43 degrees east, 9.8 degrees to the southeast. All right, so now if we were given the ability to start drawing out other strike lines, we could, for example, draw out the 1,000 strike line. So we know that this is 30 sixteenths. So let's go ahead and draw out another point that's 30 sixteenths away from this line and perpendicular to it. Okay, so we get this point over here. Now I'm going to connect this point and A, and that's going to give me my 1,000 strike line. All right, and then I'm going to go right in between these two and draw the 900 strike line. All right. Now, everywhere where that 900 meter strike line intersects 900 in elevation, 900 meters in elevation, that's where that rock would outcrop. And let's assume it's a pretty thin unit, and we're just going to try and draw it in as a line. Same thing over here. Everywhere where we see an 800-meter strike line and an 800-meter elevation, we're going to say that that rock outcrops there. And same thing for 1,000. Okay. 900-meter strike line. Okay, so and down here you'd have to assume that there's another one that's a 700 somewhere down here. So maybe we intersect it there. Now if we connect these points, we get our outcrop pattern. And I just tried to tuck it right under here at the 1,000 because I didn't really know what was happening up there. It's probably not exposed. Maybe it goes underground and then peaks back up over here and comes down. Okay, and here it's under, because this is 800, so this is 1,000. It's way underground at this point. So we wouldn't see it at the surface. All right, let's say that we want to view this along this F to D, or we want to make it a cross section from F to D. Then what we want to know, let's say we collect a strike and dip right here. Our strike is going to go along this strike line. Another pen color. Strike is going to go along the strike line. A dip is going to go down into the southeast, just like we had before. And we know that that dip was 9.8 degrees. So if we want to know how that would look along this D to F line, what would the apparent dip be? We can use our apparent dip formula. The apparent dip formula is to take the tangent of the apparent dip, and that's going to equal the tangent of the true dip times sine of beta, where beta is the angle between strike and the line you're making your cross section on. Here we want apparent dip, so we're going to do inverse tangent. Tangent of 9.8 degrees times sine of whatever this angle is. This is the line we're making our cross section on. This is the line of strike. I get 30 degrees. So we're going to solve this really quick. Tangent of 9.8 degrees is 0.17, and sine of 30 degrees is 0.5. We're going to multiply those together. And we're going to do the inverse tangent of that. And I get 4.86 degrees. So this is the apparent dip along DF. So if I were going to make a cross section, and that cross section we're going to represent what's happening in the subsurface between D and F, and let's say we have no vertical exaggeration, we're going to go let's say that's your topography. We know that we are dipping 9.8 degrees to the southeast. Along D and F, we're probably below the surface. We're not going to use this true dip of 9.8. We would use the apparent dip of 4.8 degrees to the southeast. So that might be what we draw in. Hope that helps.